Good afternoon and welcome to UT Energy Symposium. I want to start with a couple of announcements. First, some of you might be here for Dale Klein's talk. There were 2 notices sent, so there might be confusion. I just want to clarify that we are having the Student Research Showcase, not Dale Klein's talk, which has been postponed to November 29. So apologies if there was a confusion regarding that. For those of you who do not receive but want to receive notifications about this event, you could send an email to utenergysymposium@gmail.com and we will add you to the mailing list. That's utenergysymposium@gmail.com. Our speaker next week is going to be Commissioner Rolando Pablos of the Public Utilities Commission here of Texas. He will talk on regulating a hot, dry, and peaky electricity system, the inside view. He will obviously talk, as you guys know, there's just a whole bunch going on in terms of management of the ERCOT grid, and you'll hear from some of our speakers. So Commissioner Pablos will talk about that. I've also asked him to talk about the regulatory process itself. How are rules made? What are the different considerations, and how does he take all that into account and balances when he makes these decisions? It will be a great one. Please join us next week. So I would like to introduce our speakers today. But before that, I just want to say a word on what this Student Research Showcase is. This is an event, one-week event that happens every semester. It started actually last semester, and the idea is to showcase some of the best research that our graduate students or students generally here are doing, and we try to draw from all the different schools and departments. And as you will see, this represents some of the best work being done on energy globally. So we are very excited to do that. This is a platform for the students, but this also, our hope is a catalyst for some of you to explore research in the various centers, institutes, and research groups here on campus. We have 4 speakers today, all of them with extraordinary backgrounds and great research. Our first speaker will be Ashlynn Stillwell, who has a bachelor's degree in chemical engineering from University of Missouri and a master's degree in environmental and water resources engineering and public affairs from UT Austin. She is currently working on a PhD in civil engineering and holds the prestigious National Science Foundation Graduate Research Fellowship. Her research focuses on nexus of energy and water, including drought resiliency of power plants, use of reclaimed water, energy recovery from wastewater, and also wind-powered desalination. Our second speaker is, if you guys could just could wave your hands, they will be up here in a minute anyway. Our second speaker is Yezhou Wang, who is currently a PhD student in the electrical and computer engineering and works in Professor Ross Baldick's research group. He works on power electrical system modeling and operation and integration of renewables in the grid. He holds 2 bachelor's degrees, one from University of Birmingham in the UK, and second from the Huazhong University of Science and Technology in China. Both of these degrees are in electrical engineering. Our third speaker is Scott Robinson, who is a dual degree student here in the Energy and Earth Resources program in the Jackson School of Geosciences and also in the LBJ School of Public Affairs. He holds a bachelor's degree in political science from Middlebury College, where he studied the role of energy resources on U.S. foreign policy. Currently, he works on solar photovoltaic markets and policies. Our fourth speaker is Steve Bryant, who is a master's student in the Department of Petroleum Engineering, and he works in the hydraulic fracturing research group directed by Professor Mukul Sharma. Steve has worked on unconventional production in the Eagle Ford Shale, which many of you might know is a really very important development just in the last couple of years in South Texas. He has also contributed to the Energy Institute's report on outlook on unconventional gas and oil, and we are still part of that study. Prior to attending UT, he graduated in mechanical engineering from Rice University and has worked with Lockheed Martin. So let's welcome our speakers. And I'll turn the podium to Ashlynn.
Thank you. So I have this lapel mic for the recording, but it's not an in-house mic. So if you can't hear me in the back, just raise your hand and wave at me, because I'm gradually getting my voice back from an illness earlier this week. So if I'm not yelling loud enough, just let me know. So today I would like to very briefly talk to you about some of the research I've been doing here at UT over the last 5 years or so. And it's all housed under this broad category of the water energy nexus. And I'll talk a little bit about what that means. And I'll specifically talk about my PhD work, which focuses on water impacts for thermoelectric power generation. So when we say energy-water nexus, what do we mean? Well, we mean that energy and water are interrelated, very simply put. So we use water for energy. Cooling power plants requires water, and liquid fuels production, that I'm sure you'll hear more about today with fracking and just conventional oil and gas, does require water. On the other side, which is something I won't really get a chance to talk about today, is the fact that we use energy for water systems. So getting water to your house or apartment in a drinkable fashion, heated, if you like to take a heated shower like I do, requires a lot of energy to treat that water, pump it. Water's heavy. If you think about lifting up a gallon of water, it's heavy. And heating water takes a lot of energy. So this is a non-negligible part of our energy consumption in the United States. So like I said, today I'm going to talk about thermoelectric power plants. And this is a very simplified diagram of a thermoelectric power plant, but they do in fact require cooling. So what happens in a power plant cycle is you start with a boiler. Here, I'll use this pointer. We start with some sort of fuel in a boiler. So this can be coal, natural gas, nuclear fuel, biomass, solid waste from a municipal source if we want to do waste to energy, something that we are burning or reacting to generate heat. And it is boiling water in this loop to create steam. The steam then goes to a steam turbine, where it spins the turbine, creating mechanical energy. So we're going from thermal energy right here to mechanical energy in the turbine, which is then connected to a generator. Generator is a magnet rotating through electric wires. We're generating a current. That is where we have the electricity produced from the generator. So we have this steam that went through the turbine. It's ultra pure water because we don't want a whole bunch of nasty junk here on the turbine. So we don't really want to get rid of that really clean water. It's still steam at this point, so it's water as water vapor. So we condense it with a cooling tower or some other sort of heat exchange. So when we talk about water for power generation, it's really that cooling tower in the bottom right that's the focus, because you notice this steam loop is closed. It's not going anywhere. We're not losing any of that pure water. But we need water to remove the heat, to condense that back into water so we can create steam again, run through the turbine connected to the generator, and back in a closed loop. So this is oversimplified, but hopefully you kind of get the idea of why we need a large amount of water here. And you notice that there are two terms, water withdrawal and water consumption. So a lot of times people will say, power plants use a lot of water. Well, what does use mean? What does that really mean? We've drilled that down into withdraw and consumption. So withdraw, in this picture, you can see it pretty plainly. It's pulling water out of a water source. Consumption, then, is the evaporation. It's not really lost. We have one hydrologic cycle here on the globe. It's going to come down as rain somewhere, but maybe it comes down as rain in Louisiana, which doesn't really make much difference to us here in Texas. So water is then consumed as opposed to withdrawn. So this is kind of a terminology lingo that goes in with thermoelectric power plants. And because thermoelectric power plants use so much water, they withdraw and consume so much water, they're vulnerable to water constraints. And that's kind of twofold, as you can see in this particular figure. You can have water that is too much or too little. So if you think about different instances that come across in the news, you can have too much water in a flood, and it'll shut down a power plant for safety reasons. So think about Fukushima. There's this tidal wave flood of water. It's a danger to the power plant. It shuts down for security reasons and safety reasons. On the other hand, we can actually have too little water. So if you've lived in Texas for the last 18 months or so, you'll remember that last year was a pretty bad drought. And when power plants don't have water to cool themselves, they end up having to either dial down or shut down because there's just not enough water. And this happened in Texas. A handful of power plants had to dial down operations because there's just plain not enough water. So this vertical axis of this cross here is kind of a quantity constraint. And the horizontal is more of a quality constraint. We can actually have water that's too hot or too cold. So when water's too hot, a power plant can't adequately cool itself, and it needs to dial down. And there are actually thermal regulations that prevent power plants from discharging very, very hot water. So we're not cooking the fish in the stream downstream of a power plant. Kind of makes sense if you think about it. But on the other hand, water can actually be too cold for a power plant. This doesn't happen very often, but it did happen in Texas in February of 2011. If you lived here, we had some rolling blackouts that happened. Well, that's because we had a freeze. And a couple of large power plants, the instrumentation froze on those particular facilities. So the cooling tower itself didn't freeze. That's a lot of water that would be difficult to freeze, but the instrumentation did. So the instrumentation feeds back to the control system that says, I'm frozen, I'm shutting down. And when that happens very quickly, all of a sudden the grid doesn't know how to cope with that, and we have rolling blackouts to cope with supply and demand mismatches. So there's kind of this Goldilocks approach where we need to have just the right amount of water, not too much, not too little, and just the right temperature, not too hot, not too cold. So as you can imagine, this complicates resource management in terms of energy and water. So I'm here to talk about my research, and I'll just briefly touch on some of the aspects of energy and water for power plants that I'm looking at in my dissertation. And these are the research questions that I'm trying very hard to tackle. So the first one is, how do different cooling technologies affect water availability? So if you remember in that first image of how power plants use water, I had a cooling tower in there. That's where the cooling water comes in. That's where we're condensing the steam. Well, it doesn't have to be a cooling tower. It could be an open loop system where we're just using water once and discharging it. Or it doesn't even have to be wet in the first place. It could be a dry system. We could use air, kind of like the radiator on your car. But as you can probably imagine, air and water have very different heat capacities. So the ability of a dry-cooled power plant to operate as efficiently is very difficult. So these power plants that are dry-cooled have an efficiency loss. So my first question is, what do these different cooling technologies do in terms of water availability on a large scale? And kind of following on that, what's the economic value of drought resiliency? So if a power plant decides to switch to dry cooling, they have some efficiency loss associated with it. It's a very expensive system. But at the same time, if we have a really bad drought, that power plant is still running, when its neighbor that's wet-cooled had to shut down because there's no more water. So it's kind of an insurance policy. You could think about it that way. It's insurance against drought, and what's the value of that? Then on kind of a separate note, I'm looking at the dynamic impacts of water storage. So a lot of times our supply-side approach to water management is to store more of it. We'll build more reservoirs. Well, sometimes reservoirs help, and sometimes they don't. And what are the dynamic impacts of that? And lastly, I'm looking at where could reclaimed water be used for power plants. So this water use in power plants is non-contact. It doesn't have to be very pure drinking water that we're using to dissipate heat. It could be treated wastewater effluent. And in fact, that's what we do here on campus in some of the chilling stations and the cooling stations on campus. They use treated wastewater effluent from the City of Austin wastewater treatment plants. We also in Austin have the Sand Hill Energy Center that uses treated wastewater effluent to cool the power plant. So this is possible, but where is it really feasible economically and technologically and geographically speaking? So I'll just touch on these very quickly. In terms of the first question, switching cooling technologies at power plants, if there's two maps here, there's one called the full execution, one called current conditions. The difference between them is legal jargon, and it's really not important for our purposes here today. But you'll notice there are some red dots decreasing down to kind of purple dots. Red means that the water availability associated with those rights has increased more than 30% as a result of changing power plants from wet cooling to dry cooling. So there's a lot of dots up there, right? Those are not power plants. Those are other water users that are taking advantage of power plants using less water. So in this particular basin right here, this is the Brazos River Basin, there was only 9 power plants that we modeled in that basin, but there's a lot more than 9 dots up there. So power plants are an appropriate target for water management strategies, is what that means. When we talk about the economic value of drought resiliency, it comes down to the expected value of how much a power plant would have to dial down. So if a power plant uses dry cooling, they will incur about a 2 to 5% on average efficiency loss. Well, what we've shown here is that the expected value of curtailment is about 2.5% or so. So if you're a wet-cooled power plant, you can expect to have to dial down throughout the year about 2.5%, which is kind of close to dry cooling. So we're not actually jeopardizing any of the grid integrity by switching to dry cooling, and it can be an insurance policy against drought. Moving on to water storage. If we incorporate storage into power plants, so giving them an extra supply of water in terms of a drought or some sort of supply interruption, you would think that would be really good for the power plant. But what does it do to everyone else in the basin? And it really depends on how water is allocated. So again, here is the Brazos River Basin. Here's the Colorado River Basin. And the warm colors in the Brazos River Basin show that actually incorporating more storage at power plants can be beneficial for everyone because there's more water that's being stored in the system. In the Colorado River Basin, not so much, because a lot of the water is allocated to other users. So if we incorporate new storage, we're actually just taking water from someone else to fill up a brand new lake. Hopefully that idea kind of makes sense. It goes along with this idea of a closed basin and a zero-sum game, so to speak. So we have to think about all of these things in connection instead of just making isolated decisions. And lastly, this is something I'm working on right now, of opportunities to collaborate between power plants and wastewater treatment plants. So a lot of the power plants, the thermoelectric power plants in Texas, are within 5 miles of a wastewater treatment plant. Generally, the power plants are where the people live. The wastewater treatment plants are where the people live because we're generating wastewater. So 135 of about 190 facilities in Texas are within 5 miles. So this is good, geographically speaking. And in terms of flow requirements, there's enough wastewater for almost all of those power plants. There's only 15 power plants that don't have sufficient flow somewhere around them from wastewater treatment plants. So this is a promising idea that maybe we don't need to be using fresh water and drinking water for our power plants in the future, in terms of managing both water and energy in a symbiotic, sustainable fashion. So that's all the time I have, and I think we're taking questions at the end. If you have questions specifically for me, here's my contact information. If you're interested in anything that I did not get a chance to talk about in depth today, go to that website, and you will find all of my research. And if you go to weberenergygroup.com, you'll get all of my colleagues' research. And you can find out about some more exciting energy stuff going on campus. Thank you.
Good afternoon, everyone. My name is Yezhou Wang. I'm currently a third-year graduate student at Department of Electrical and Computer Engineering. And I'm going to show you some of my research about power electrical system safety and security. When we talk about safety and security, what we really talk about is how to keep your lights on. Well, that particular question is quite simple. The answer to that question is sometimes really, really challenging, and I'll show you why. So today's presentation, I've got some sections. First of all, I'll give you a very brief overview of what is power grid safety and security. And then I'll show you some examples of what is so-called a cascading outage. And the example is really interesting. It showcases the 2003 Northeastern blackout in the United States and Canada. And thirdly, I will show you some of the research that we have done to tackle that particular problem, which is having a product called Cascading Outage Analyzer. And then I will talk about the future work, what kind of questions we're trying to answer, and then we will take questions hopefully after everybody has done their job presenting. So everybody wants to keep their lights on, no matter what, right? We have this beautiful auditorium, and we want to have the lights on. And no matter it is raining, it is snowing, it is shining, it is dark outside, it is bright outside, we want to have these lights on. But for the first 20 years of my life, I always think that this is for granted. We should have this, and it's easy to have this. However, it is not actually easy. Why is that? Because power electric grid is the most complex system human being has ever created. And it is extremely hard to operate. And I'll give you a picture sort of roughly to show how complicated is that. And second point is that power system operation is subject to a lot of threats. Imagine that we have so many transmission lines, so many generators, so many plants, like so many feeders, so many small power poles, and they're all subject to a lot of threats, such as natural disasters, hurricanes, tornadoes, earthquakes, lightning, everything. And in the recent 2 decades, we are more focused on the terrorist attacks because we discover that if somebody who is really bad, they can plan an attack on our power system that makes our lights off. And this is a picture sort of to show how complex it is. The picture on the left-hand side is showing that the North America power electric interconnection. And they have actually 4 interconnections. When we talk about United States, we have 3, which are Western Interconnection, Eastern Interconnection, and Texas Interconnection. I'm really proud that I'm in Texas because we're in a state that has its own interconnection. In other words, what happens in the northeast part, what happens in New York City, what happens in LA, doesn't really matter about the lights in our home. And if we are dark, they don't really care about us as well. The picture on the right-hand side is the ERCOT, or Texas Electric Transmission Grid. As you can see, you can probably very hardly see any of the detail in that map. But I'm just showing that map to you that we have so many transmission lines, so many dots in it, that make sure that our power is transmitted from those huge power plants, from some wind turbines, from solar PVs to our homes. And it's a tremendous job, and it's really hard to operate. Then, what are those threats? 2 typical ones. The first is the damage at Fukushima nuclear plant at Japan that we all know about due to the huge earthquake. And the second one is the damage picture after Hurricane Isaac just happened in New Orleans. And all these kind of natural disasters will destroy some of the facilities of our power system. And our power system is sometimes very vulnerable to those kind of threats. For example, every time we have a large hurricane like Isaac, like Katrina, like Ike, we always experience or we expect some power blackouts, right? Rolling blackouts, sometimes we just don't have lights. But as engineers and researchers, we want to really make sure that those blackouts don't happen. So I will give you an example about how severe those outages are. The first example I'm going to give is a 2003 example of the northeastern blackouts in the United States and Canada. It happens in 2003, August 14th and 16:05. And over 50 million people were out of power in northeastern United States and Ontario, Canada. And 61 gigawatt of power was lost. How much is 61 gigawatt? The peak demand in Texas last year was actually 68. In other words, you can imagine as much as the whole Texas is blacked out. That kind of scale at 2003. And those places infected include, as you can see from the right-hand satellite picture, Albany, New York, Buffalo, Toronto. You can see that Toronto is actually whole dark. So this is really something tremendous. And it really creates chaos in the societies and really affects our lives. But how does that happen? Well, as we can see from this picture, it shows the path of that particular event. And you can see the trip time at the right-hand side of that table. It goes from 1605.57 until 1610.38. Altogether, 14 high-voltage transmission lines are tripped off automatically. And those places range from Ohio State to the west part of the Michigan. And that's huge. How can we prevent that? First of all, we're going to know how it spreads out. What is the path? So some people might say that the 2003 blackout is isolated and is rare, but it's not. We have so many blackouts. Last year, we had a blackout of the rolling blackouts in the Austin area due to the cold weather. And we have a lot of different blackouts. Some of the most severe ones include the India power grid's collapse just 1 month ago. And it's affecting almost 10% of the world population. In other words, 600 million people were out of power for a couple of days. Can you imagine that? It's really severe and it's really bad. Okay, so we really need some tools to analyze these events and find ways to prevent them. That's why we created this, the Cascading Outage Analyzer. What it does is that if you give me some certain initial disturbances, then I will tell you how the system go blackout. What's the path? And if we can see those paths beforehand, we can strengthen those ties and prevent those really bad blackouts. I have a demo here. This is a system called IEEE 118 bus system, and it has a lot of lines and a lot of buses. And if we have initial disturbances at some particular points where you see the arrows, then the system will black out at different stages. So this is the first stage, and it has like 3 lines out, and then some more of the lines showing yellow out, and third stage, 1 more line out, and fourth stage, some more lines out. And then the system just collapsed. You're in dark, right? So this analyzer is sort of telling us if there's some disaster like some hurricanes or some tornadoes, how are we going to prevent this kind of cascading outage to happen, right? So now we have this kind of analyzer. What can we do? We can identify the worst case scenario of the cascading outage event given certain disturbances. We have to differentiate the consequence of natural disasters and possible terrorist attacks. And we have got a lot of researchers on that. And then we have some short-term impacts like cascading outage, where basically the facilities are not out. They're just not producing power due to automatic tripping. And there are some long-term impacts like natural disasters, like earthquakes, really getting that kind of component out of the system. And then we could have more accurate and detailed model of the power system. So with those future work, I think we can really secure our grid and make everybody's lights on all the time. So that's my presentation. Thank you.
All right, guys. First of all, welcome to the UT Energy Symposium. Thanks so much for coming. My name is Scott Robinson. I work for the Energy Systems Transformation Research Group right here at UT. And I'm going to be talking to you today a little bit about residential solar photovoltaics. If you talk to somebody, an advocate about solar PV, they're usually pretty excited. They're excited about the potential carbon benefits. They're excited about energy security. They're excited about reliability, pretty much everything. What you don't get a whole lot of is the downsides. In other words, if solar is so great, why don't we all have it on our roofs? So that's what I'm going to be talking to you a little bit about today. First of all, just a quick introduction into the market. The residential solar market makes up about 30% of the larger solar market in general. And of that residential part, we have about 133 million potential housing units. It's quite a lot. If every one of them had solar panels, that would be a lot of gigawatts. Okay? However, only 25% of that is available because there's shade. Some structures, as far as roofs, aren't really built for it. Solar resource isn't great some places. So we've got about 25% of that to work with. The installed capacity right now is about 2% of that 25%. Pretty small. But we've got a lot of working room. That's what the advocates of solar power will tell you. It's like, look at the size of that market, right? But again, I'm trying to see, like, why aren't those people installing? Well, there are these large barriers to adoption. Solar is really expensive. It's not very efficient. That's kind of the technical aspect. But then over here on the left side, that's kind of what I'm interested in. These non-technical, non-financial variables. These barriers are pretty important, and what I want to highlight is that for consumers, if you're looking to buy PV, it's all cost and benefit. I get a certain benefit, and I have certain costs. Biggest cost is obviously the upfront capital, but attributing to that are these non-financial barriers that prevent us from adopting. So to look at these barriers, we can't really use dollars and cents right now. So instead, as a proxy, we use time, because everybody knows time is money, right? Before I get into exactly the nuts and bolts of our research, the data that we have is excellent. And that is thanks to the man sitting right here in the front row, Dr. Varun Rai, as well as Jay Zarnicki, Frontier Associates, Encore, Austin Energy. All these guys made this research possible, so we thank them profusely. As you can see, most of the adoptions, most of the PV is located in and around Austin and in the Dallas-Fort Worth area. Our sample is about 365 adopters, so that's quite a lot, a big share of the market in Texas right now. So we can have pretty high confidence in our model. And again, we're looking at time, particularly the decision period. How quickly somebody moves from the idea, oh yeah, solar's pretty cool, I'm interested in it, to I'm deciding to install solar tomorrow. The length of that time is pretty variable, and we're interested in trying to figure out what exactly are the drivers. To do that, we're using econometric analysis. That means regression. Here's a basic graphic of what our results look like right now for this one model. A quick word about the independent variables that you're going to see on the top. We're pretty confident in those variables right now as being the primary drivers of decision time. In order to get those, we went through our initial hypothesis generation, came up with these variables, and then tested them for robustness with sensitivity analyses and also a best subsets procedure in SAS that basically we had 124 rounds of this process. Each round evaluated simultaneously and optimized 124 models, or sorry, 1,024 models. We had over 100 independent variables to work with. We came up with these four as being consistently the best predictors. And they're the ones that we hypothesized, so we were pretty happy about it. Really quick, going down the list, what we see here is the length of your decision period. The range was between just a few months and over 60 months to decide. The average was about 9 months. Have you ever taken 9 months to decide about something? That's pretty long, right? Even new cars, things like that, don't take quite that long. So we're interested in what the reason for that and any potential levers that we have. First of all, people that thought that they were installing solar because it was a financial investment. They're chasing that return on their investment, right? Looking at the IRR. Those kind of people take longer than average to install solar PV. About 3 months on average. Second of all, peer effects. Basically, if I'm looking around and I see other people around me and in my neighborhood that have PV, I gained confidence and motivation to install it myself. People that felt that peer effect, on average, decided much quicker to install. And finally, one layer down is neighborhood contact. You have that PV around you. You take the initiative and go and talk to somebody about PV and how effective it is and all those kind of things. The finances, probably. Lastly, lease versus buy. The leasing model right now has emerged as a big leader in the solar PV market. People that lease have less risk to deal with as far as equipment, as far as warranty, maintenance. They also install quicker. The length of the bar is the number of months on average that you can decrease through these various levers. So kind of putting things together a little bit, I'm going to look at, kind of drill down a little bit on peer effects and neighborhood contact. We modeled peer effects. What are the drivers of this important variable that we discovered in our first model? It turns out it's really simple. It's the number of systems in the neighborhood. Really straightforward. But the implications are huge. If there are more people in your neighborhood with PV, they generate electricity and they generate peer effects. Those peer effects, in turn, decrease the decision times of everyone around them, making them more likely to install themselves. Or not more likely, sorry, but to have quicker decision times, possibly lowering the cost, which in turn puts more systems on the ground, which adds to that effect. They're seeing right here, they move up the scale into the power of peer effects, right? So not only do you have more systems on the ground, more people talking to each other, but every single other person who's talking to them installs faster than the last person or goes through that decision period quicker. So this is a positive feedback loop, and this research has pretty much been the first to discover this. It's hard evidence for peer effects happening in solar PV. It's pretty exciting stuff. And as you can see here in Austin, neighborhood influence on the decision to install is increasing exponentially. And again, that's, we think, because of this positive feedback loop that's occurring. So anyways, that's it. Thanks for listening, and welcome our next speaker. Thank you.
Hello, everyone. My name is Steve Bryant. I'm a master's student at the Petroleum Engineering Department under Dr. Mukul Sharma. My research topic is in the hydraulic fracturing group, specifically in refracturing, and that's subsequent fractures after a well has already been hydraulically fractured. Now, imagine there's a good amount of you who have heard about hydraulic fracturing and shale recovery in the news. So I'm going to spend most of my time actually giving a background about shale recovery and hydraulic fracturing. And then I'll give a little taste of why we're looking into refracturing after that. All right, on this map, you see the major shale plays across the continental U.S. By far, the biggest ones and most prolific at this point in time are the Eagle Ford Shale, which I worked on this summer, and the Bakken Shale in North Dakota. The Eagle Ford is just outside San Antonio, about an hour south, an hour east. It is a long spread, as you can see in this map. Both of these shale plays are now producing about 500,000 barrels per day. Before the Bakken went online, North Dakota had about 100,000 barrels a day. So by producing the shale formation, it basically multiplied that production by 5. A very large increase. Another very interesting thing is that now the shale stuff is covering about 20% of domestic U.S. production. About 10 years ago, it was thought that recovery from shale was impossible. Geologists have long known that there's a significant amount of hydrocarbons that are in shale formations. Indeed, they thought it was actually the source rock that fed some of the conventional reservoirs. So they've known about it for a long time, but it actually hasn't been possible until the last 10 years. Now it's rapidly come online, and now it's about 20% of our U.S. production. And that's just in these two shales too, the Eagle Ford and the Bakken. More are coming online, and more are being explored on a very rapid pace, including the Utica Shale in the northeast, and Marcellus Shale, and other formations around. So let me begin by giving a brief introduction about how you produce these formations. hydraulic fracturing is talked about in the news as if it's a completely recent phenomena. Now, the scale that is used is completely recent. However, the first hydraulic fracturing job was conducted actually in 1947, very long time ago. And the technology and like the fracturing fluids and the proppant that's been used and the models have been built up since then. It wasn't until hydraulic fracturing was paired with horizontal drilling that we started able to target these shale formations. Horizontal drilling also has a long history, like throughout time, but it only has become economical within the last few decades. And by pairing the hydraulic fracturing and horizontal drilling, you can unlock the shale formations. So how do you actually go about hydraulic fracturing treatment? What you're seeing in this graph is the length of a vertical wellbore going down into the earth, and then it turns horizontal at about, well, it depends on where the formation is, sometimes about 10,000 feet, sometimes about 5,000 feet. At the very top here, you can see a zoomed-in graphic of where the deepest aquifer layer is, the deepest water table. So to create these fractures, you pump in fracturing fluid at very high pressures, maybe around 7,000 psi or so. The pressures are so high that it actually splits open the rock. This is important because without splitting open the rock and creating multitudes of tiny fractures, you can't cause flow from the rock into the fractures into the wellbore. We're talking about shale formations, but what is shale? Shale, geologically speaking, is just a description of the particle size in the formation. So it's really tiny particles that are packed together. When you're talking about it in shale plays around the U.S., you're not actually, it's not truly shale all the time. Sometimes it has different types of rock in it. But what it really means when you hear about shale is that it's extremely tight. It's tightly packed, and it's very difficult for natural gas and oil to flow through this rock into the wellbore. So by creating these fractures, you're basically creating small pathways in which the natural gas and oil can move into the fractures and therefore move from the fractures into the wellbore and then up to the surface. All right, so when you fracture, looks like we're missing some images here. Okay, when you first fracture the shale, you basically pump fracturing fluid at high pressures, and this opens up the rock. Those fractures are then completely filled with the fracturing fluid. However, eventually you're going to flow this fracturing fluid back, and as a result, you pump in what's called proppant. Now, there are a lot of different types of proppant. Like you can have aluminum bauxite if you want to be really fancy, but typically it's actually just sand, common sand. Like EOG is producing in the Eagle Ford, and they actually have their own sand mines that they ship in sand and pump it down. And the reason why you do this is because when you flow back the fluid, the rock is going to close everywhere. That rock still has really highly compressive forces that are pushing down on these fractures. And when you move the fluid back and remove that pressure, it's going to try to close. It's going to close everywhere except where you have proppant. That proppant props it open and holds that in place. All right, so that's basically how we've been producing out of these shale formations in the U.S. Now, my research is about refracturing, the potential of going back into wells that have already been fractured, maybe 4 to 5 years later, and drastically increasing the level of production, hopefully to the level that it was at initially. Now, underground, think about this. You're at 14,000 feet. Imagine you're like a tiny little grain at 14,000 feet. You have the entire overburden above you pushing down on you. It's kind of like if you go to a really deep pool, you can feel the pressure. It's the same thing. All the forces down there are compressive. There's actually 3. In addition to the overburden stress, you have horizontal stresses, one in one direction, one in the other. Now, when you pump in the fracturing fluid at really high pressures, what it's going to do is it's going to try to go in the path of least resistance, right? If you're taking any physics, that's pretty much how the world works. It goes in the path of least resistance. So it's going to, in doing so, it propagates down the direction of maximum horizontal stress. That's because if you have a fracture going in one direction, it opens the rock in the other one. And this is where the minimum horizontal stress is. If you're opening the rock, you're only going to be able to do it where it's the easiest to open it. And so that's that direction. Now, when you put in a fracture into the rock, it actually changes that stress regime. So what you're seeing here in this graphic, the bottom you have the horizontal well. This is going down. This is a previously created fracture. These lines are the direction of the maximum horizontal stress. So when you put in that fracture, you split the rock, and that also changes the stress regime. Right around that split rock, it gets really, really tight. And it's not going to want to go in that direction anymore. As a result, if you take a look, the direction that a subsequent fracture is going to go in a different direction. And the reason why we're interested in that is because it's all about contact with the reservoir. You make these fractures because it contacts more parts of the reservoir. You drill the horizontal well because instead of having just one small hole, you have a hole that travels 10,000 feet. It's all about contact with the reservoir. So a subsequent fracture would propagate in a new direction, therefore contacting more parts and increasing production. Did not know. In the bottom left graph, what you see is the ideal situation. Is that it's going to go back to your initial level of production. What's interesting too about production from horizontal or from shale plays is that the vast amount of the production you get is from the first few months. It quickly drops down to a very low level. But if you can get another peak in there, you're almost doubling how much production you can get. So the work that I took over was basically trying to figure out which wells you would ideally want to fracture or do a refracturing treatment for. So you look at different things like how easily you can have this stress reorientation, things like that. And you produce an algorithm to try to do that. I'm expanding the work by trying to figure out the ideal completion technique to do this. So because you've already fractured the well, it's difficult to go back in there and fracture it again. And I'll be working on a few different techniques and agents and also try to model it so I know which time is the ideal time to do this refracturing treatment, what are the proper chemicals you use, what are the proper agents you use, and what's the proper procedure for doing that. And that's what I'm going to try to model. And the idea is to hopefully produce more, have a higher recovery factor from these reservoirs, and produce as much as we can. And that's it.
We have about 10 minutes for questions, and what we're going to do is pass around the mic. Please speak into this mic. This is not connected to the microphones, but connected to the video, so we need you to speak into this, and try to speak a little bit louder so that others can hear your question.
So I have a question about both fracking and refracking. When it comes to the disposal of fracking fluids, at times it would leak out of the rock formations and go into abandoned old wells or even into aquifers. So is there any way to increase the safety of that process in both fracking and refracking?
Yeah, for sure. I mean, the environmental questions, I guess, take the mic there. Right. Yeah, the environmental questions are huge, and that's what most of the media coverage is on. And that's a very, very important part of production from shale reservoirs. That's not my part of the research, but I am pretty familiar with it. Most of the environmental impacts actually occur at the surface. And because they're at the surface, they're relatively, you can't control it. Now, it becomes more of effectively doing operations correctly. So in direct answer to your question, yes, there is a way, and that's by having lined pits. The pits that they use for the fracturing fluid need to be lined with materials such that it prohibits it from getting into the ground and then getting into aquifers. So there is a way to do that, but it comes down to companies making sure that they do it appropriately, having the right level of regulation to make sure it is done correctly. And then the same thing follows for the other environmental concerns with shale production.
I just had a quick question for the first speaker on water. Sorry, my question is about here. I'll stand. Your last slide, you went through it really quickly. You showed a proximity of the power plants versus municipal water treatment systems. And you were assessing the flow and the adequacy of that flow for those systems. Could you explain that a little bit more? Were you saying they had raw flow that could be routed into there, or they had sufficient output, or they had sufficient amount of water? What's the difference there between flow and availability?
Sure. That's a really good question, and it's something that I'm working on right now. When I say flow, I mean effluent from a wastewater treatment plant. So the amount of treated wastewater effluent that would be coming out of a municipal wastewater treatment plant that could then cool a thermoelectric power plant. And of course, it's not just confined to geography and flow. The main characteristic that I'm looking at also is economics. So that seems to be economics and operational problems are the main reason most power plant operators are not keen on the idea of using treated wastewater. Plus, there's just kind of an ache factor of being close to your own waste, even though it's not your own waste. It's been treated. It's safe to be around humans, but there's still just kind of a knowledge gap to go in there. So you're right that that's kind of vague. That was more of a back of an envelope calculation, and I'm drilling down to individual facilities and are there appropriate ways to match up individual facilities? Because ideally you would want to go from one power plant, one wastewater treatment plant to one power plant. But there are other options. So for instance, the Palo Verde nuclear power plant in Arizona, it gets treated wastewater effluent from something like 6 wastewater treatment plants. And that's its sole source of cooling water. So there's plenty of options. That's what I'm doing right now. I'll get back to you in 6 months with a better answer. How's that?
My question is about the grid. So, of course, we've got a very antiquated grid. We haven't invested very much in it, but now that when we do invest in the grid, it's almost all smart grid technology, you know, bringing more things online, which actually, of course, creates more entry points for someone who had malicious intent to do something bad. So how do you reconcile a smart grid with a safe grid?
Well, are you talking about
specifically around like power generation facilities?
Power generation facilities? Mm-hmm. Well, in terms of generation, I would say if you have more smart grid technologies that enables more distributed generation, in other words, you have more small or microgrids running around particular loads, like this building you have on generation, then will be more secure towards getting power from some power plants like 300 miles away. However, if you have more facilities, it's more likely that you need to communicate more. You need to get more data in and out from the grid. In that sense, it raises a question about how secure is the communication, or how do we prevent the cyber attacks on those data privacy issues. In that sense, there are a lot of researches ongoing about that SCADA system security, and we have a lot of different measures to do that. But this is really particularly interesting and challenging and new question, and we have been exploring that alternatives a lot.
My question is for Scott. That two quick questions. The first one is, how do you know when a person decides, hey, I wanted to buy a photovoltaic? And the second one, if you consider in your analysis the number of companies that are selling this stuff in a particular region. I guess so.
Yeah, to answer the first part, it's pretty straightforward. We just ask them. First of all, when were you first starting to get interested in PV? And an additional question, when did you install PV? And then we take the difference. And as far as installers, could you repeat the question again one more time?
How many different companies offer PV in a region? In each region?
You know, off the top of my head, I couldn't tell you. There's quite a few, and I would say there's probably more in Austin.
So I was thinking, okay, if in a particular region there is a lot of competitors, maybe the people want to buy more because there's more marketing or whatever reason. In another, there's just one. So that was.
Yeah, absolutely. And a lot of the research that we're doing right now has direct implications for installers and marketing and how they want to push their technology onto potential consumers. And
I have a question for Steve. Two questions, actually. If you said it, I missed it, but what's the recovery rate from refracturing? And are you going to cause any earthquakes when you refracture?
That's a good question. Both of them, yeah. Recovery rates, you know, there's not really any known values. It hasn't been done a whole lot. So the idea would probably be move it from maybe a 20% recovery factor to hopefully a 35, something on that scale. But that's unknown for sure. About the earthquakes, geologists have looked into this, and their guess and their hypothesis is that earthquakes are more often to be caused by water injection wells. So you produce water when you produce in conventional oil and gas as well as in shale production, and then you pump that water back in. And the idea is that over a long period of time, because this happens over hundreds of days, that water buildup is more likely to cause the earthquakes. That definitely is a question for a geologist. It's not something I really could answer technically, but I take them at their word for it. So no other choice really.
My question is for you, Steve, as well. I was wondering, when you refracture, are you using the same route to get to the rock at a different point, or how does that work?
Yeah, so it's actually the same well, and it's pretty much everything's the same. That you pump in the fluid down the same vertical well. It goes through that same horizontal turn. The only difference is that it's a much more controlled process in the first time around. The first time around, typically you have steel casing that lines the entire horizontal well. You plug off a section of that casing and you perforate, you generate holes in the casing, and that's what the fractures go through, or that's what the fracturing fluid goes through. The second time around, you don't really have the option to plug everything off in sections. So you have basically a lot of perforations along that horizontal portion, and you also have fractures that are created from those perforations. And then you go back in and you pump it down a second time. So you potentially have access to every single fracture that was created the first time. It requires more fluid, and it's also a good question of what will be growing. And that's the question I actually will be working on. Like, which fractures will grow? Will all of them grow? How do you plug them off if you want to plug them off? So that's what I'll be looking at.
Thank you.
We have time for one more question.
A question for the first speaker. I noticed on your map you just focused on surface water. Have you looked into groundwater at all and any kind of exploration into use of brackish water?
Yeah, so he asked about that I'd only focused on surface water in my particular analysis, and asking if I'd ever done any work with groundwater or brackish water in particular. I haven't. There are a handful of power plants in Texas that use groundwater for cooling. They're mostly in Panhandle area because that's where groundwater is plentiful and surface water is not. A certain element of my analysis that I didn't get a chance to touch on today was the legal ramifications of water availability. And even though groundwater and surface water are highly interconnected, we don't think so legally in Texas. So surface water is completely independent of groundwater in terms of law and availability in those terms. So that's the main reason I focused on surface water only. It is possible. It's obviously possible to use groundwater because a lot of power plants do it. It's possible to use brackish water. The challenges there are materials, because the salinity of water will pit concrete or steel or those sorts of materials, so you have to get more expensive, more sophisticated materials. And disposal. What do you do with the water after you've used it and it's heated up? So you can't just put it in a stream because the salinity is high. You could re-inject it into an aquifer. That has an energy penalty associated with re-injection. So there's some challenges there, and I don't know of any facilities that use brackish water for cooling, but it is possible. There are coastal power plants that use seawater. So it's an option. It's just there are unique challenges associated with it in an inland sense. Does that answer your question?